We tend to think of everyday digital documents, especially something as common as a PDF, as being pretty, well, static, uncomplicated.
Right, like it's just the digital version of a piece of paper.
Exactly. But what if I told you that even these seemingly simple files can actually conceal secrets right under our noses?
And we're not talking about standard encryption here, are we?
No, not at all. It's something more clandestine, the art of hiding information in plain sight. Steganography?
Steganography, concealing the existence of the message itself, not just its content.
Precisely. And today, we're diving into a really ingenious variation, distributed steganography, specifically within PDF files.
Distribute it, so splitting the secret up.
Yeah, picture this. Taking a secret, breaking it into pieces, and then hiding those pieces across multiple separate PDF documents.
That's fascinating because standard steganography tries to make one carrier file look innocent, right? But distributing it adds another layer entirely. Makes detection way harder, I'd imagine.
That's the idea. So in this deep dive, we're going to unpack this technique. You'll get how it works, the subtle ways it plays with the internal structure of PDFs, and the security implications.
It's one of those things where understanding the tech underneath is crucial. The aha moment, like you said.
Definitely. Prepare for that moment when you realize a file format you probably use every day has these hidden depths. And our guide is a really insightful research paper that gets into the nitty-gritty details.
Okay, so let's start with that foundation, how PDFs are actually built. Because they aren't just flat files, are they?
No, not at all.
They have a very specific structure. Think of it like, well, the paper uses the analogy of a book. There's a header saying, hi, I'm a PDF version X.
Right.
And you have the body. That's where the actual content lives. Text, images, graphics, but as individual objects.
Objects.
Yeah, each piece of content or instruction is an object with its own unique ID number.
Okay, so the body isn't just one big block of text and pictures.
Not at all. It's a collection of these objects. Could be simple things like true or false, numbers, text strings, but also complex things like data arrays, dictionaries defining properties, and even binary streams for, say, compressed image data.
And these objects have IDs. How does the PDF reader, like Acrobat or whatever, find them?
That's where the cross-reference table comes in. The ETS table, it's like the book's index and table of contents rolled into one.
Okay.
It lists every object's ID, and crucially, its exact byte offset its location within the file so the reader can jump straight to it.
Interesting. Does the order in the XREF table match the order we see things on the page?
Not necessarily, and that's potentially important. The order objects are listed might not reflect the visual flow at all.
Okay, that hints at some flexibility, maybe some room for manipulation there.
It certainly does. Then, after the XREF table, you've got the trailer.
The trick.
Yeah, it's super important. It tells the reader where to find the root object, the top-level object that sort of organizes the whole document's content. It also states the total number of objects in the file.
So the reader starts at the end, finds the trailer, finds the root, and works its way back.
Pretty much. The trailer points to the start of the XREF table via an offset. The reader parses the XREF table, finds the root object's location from the trailer info, and then follows the links or references from the root object to all its children. The pages, fonts, images, and so on to build what you see.
Got it. Header, body with objects, XREF table, trailer. Oh, and you mentioned an end of file marker.
Right, %EOF. Just
Yeah.
tells everything, stop here, that's the end.
Okay, solid foundation now. The core technique from the paper. How do you actually hide a page using this structure?
It's quite clever. It involves manipulating the object tree, specifically something called a pages object.
A pages object.
Yeah.
Does what it sounds like.
Essentially, yes. It represents a collection of pages. Inside it, there's a kids array, which is basically a list of references pointing to the individual page objects. And crucially, there's also a count value that says how many pages are in this collection.
So the count is the official number of pages the reader should expect.
Exactly. So the main method is to mess with this. Two main ways described. First, you can actually remove the reference to the page you want to hide from that kids array. Just delete its entry.
Okay.
And at the same time, you decrease the count value by 1. So if it said count 2 and listed 2 page references, you change it to count 1 and remove 1 reference.
Like kids ref A. Ref B count 2 becomes kids ref account 1.
Precisely. The paper gives an example just like that. They noted this method slightly decreased the file size, which makes sense.
So the page object itself, the data for that page, it's still physically in the file.
Yes. It's just orphaned. The reader follows the kids array, sees only 1 reference, reads the count as 1, and just never knows the other page object even exists. It's like tearing a page out of the table of contents, but leaving the page in the book.
Wow, okay. And the second method?
Even simpler, apparently, especially if you're hiding pages at the end of the document sequence. You just decrease the count.
You don't touch the kids' array?
Nope. You leave the references intact, but just tell the reader there are fewer pages than there are references. So kids ref A, ref B count 2 just becomes kids ref A, ref B count 1.
And does that cause an error?
You'd think so, but the researchers found this works surprisingly well. And the big advantage, 0 change in file size. They called this method more silent.
That is sneaky. Did they test this across different PDF viewers?
They did. They tried Evince, Adobe, Acrobat X, Ocular, Firefox's built-in viewer, even graphics programs that import PDFs like GIMP and Inkscape. All of them correctly showed the reduced page count. The hidden pages were just gone from the user's perspective.
Incredible.
Yeah.
Any glitches? You mentioned Acrobat X.
Yeah, Acrobat X was the slight exception. It's known for being quite strict in how it parses PDFs. Sometimes, after opening a file modified this way, it would prompt the user to save changes, even if they hadn't done anything.
Why?
The researchers guessed it might be detecting that orphaned objects, the unlinked page, and wanting to fix the file. But crucially, it still displayed the reduced page count. It didn't reveal the hidden page.
So even the strictest reader didn't blow the cover, just acted a bit weird.
Right. And they also tested with PDFTK, a command line tool, which also correctly reported the lowered page count.
So this hiding method seems pretty robust
Yeah.
and efficient too, right? Doesn't take long to just change a counter.
Exactly. The paper notes it's a constant time operation. Doesn't matter if you're hiding 1 page or 50, changing that count value takes the same tiny amount of time. Very practical.
Okay, let's make this concrete. How would someone actually use this? Say, add a secret page to an existing PDF and then hide it.
The process they describe is pretty logical. First, you need your carrier PDF, the innocent-looking one, and you need another PDF that is your secret page or pages. Step 1 is to merge them. They use PDFTK for this, but mentioned tools like PDFjam or even just printing documents together to a new PDF file could work.
So you end up with one PDF that has, say, the original 5 pages plus 1 secret page for a total of 6.
Correct. An interesting side note, they found the merged file might even be slightly smaller than the 2 originals combined because of how PDF objects can be shared or optimized during merging.
Okay, so you have the combined 6-page file, now the hiding part.
Now you apply the technique. You go into the PDF structure, find that pages object, and either remove the reference to page 6 and change count from 6 to 5, or if page 6 was the last one added, maybe just change count to 5.
The goal being that the final file looks and acts exactly like the original 5-page carrier document.
Precisely. The paper has a figure illustrating this flow. Start with carrier, add secret, then hide the secret page by tweaking the structure.
And this is way better than, say, hiding white text on a white background.
Oh, absolutely. The paper explicitly contrasts it with those kinds of tricks. White text gets revealed if you accidentally select it. Overlapping objects can sometimes be selected or detected. This structural hiding, it's much cleaner. The page just isn't part of the document structure anymore, so standard interactions won't reveal it.
Okay, that covers hiding a single page. But the title mentioned distributed steganography. Where does that come in?
Right, that's the next layer. It involves combining the PDF hiding with techniques called secret sharing.
Secret sharing, like splitting a password among friends.
Sort of, yeah. The basic idea is you take your secret information and mathematically divide it into multiple pieces, or shares.
Right.
The clever part is how these schemes often work. You usually need a certain number of shares, a threshold, to reconstruct the original secret.
So maybe you create 5 shares, but you only need any 3 of them to get the secret back.
Exactly. That's a threshold scheme. It adds resilience. If you lose a couple of shares, it's okay. You can still recover the secret.
How do you actually split the secret?
The paper mentions a simple method using the XOR logical operation. You could convert your secret, say hello, into numbers like ASCII codes. Then you generate some random numbers and XOR them with your secret numbers to create share 1. Generate more random numbers, XOR again, create share 2, and so on.
And to get hello back,
You'd XOR all the shares together. The random parts cancel out, leaving the original numbers. Though with simple XOR like that, you usually need all the shares.
I see. Are there more advanced ways?
Definitely. They briefly touch on threshold schemes using polynomials. Imagine your secret is encoded as a coefficient in a polynomial equation.
Like in algebra class.
Kind of. You define a polynomial, say a quadratic degree 2. Your secret is part of that equation. Then you calculate several points on the curve defined by that polynomial. Each point, its x and y coordinates, becomes a share.
Mm.
Now, the magic is, for a degree 2 polynomial, you only need 3 points, 3 shares, to perfectly reconstruct the entire curve and thus recover the secret. Even if you generated 5 points initially, any 3 will do.
That's clever. So you get that threshold property.
Precisely. And they note there are many other algorithms for secret sharing, supporting different types of secrets and offering different features.
Okay, I think I see how this connects now.
Yeah.
You take your secret, use a sharing scheme to split it into, say, 3 shares.
Right.
And then you take each share, make it into a PDF page, add that page to a different innocent-looking carrier PDF, and then hide that page using the structural manipulation we talked about earlier.
You got it. That's the distributed steganography process. Each share is hidden inside a separate PDF file by making it an invisible page.
Wow. Okay, so how do you get the secret back? That sounds complicated.
It involves reversing the process, naturally.
Yeah.
First, you need all the carrier PDFs that hold the shares, or at least enough of them to meet the threshold if you used a threshold scheme.
Okay.
Then, for each PDF, you have to perform forensic analysis to find the hidden page. Remember, it's not visible in a normal reader.
How do you find it? By looking for orphaned objects or discrepancies in the page count.
Exactly. Once you identify the object ID of the hidden page, you need to trace it to find its actual content.
And that content is the share. Is it just plain text?
Usually not. The paper explains page content is often stored in binary streams, marked by stream and endstream keywords. And these streams are frequently compressed to save space.
Compressed, like a zip file.
Very similar. A common filter mentioned is fleet decode, which uses the same zlib compression algorithm as zip and gzip. The object definition tells you if a filter is applied.
So find the hidden page object, find its content stream, check if it's compressed, decompress it if necessary.
Right. And then you extract the actual data, which represents the share. The paper walks through an example recovering hello split into 2 shares in 2 different PDFs.
What did the decompressed data look like?
It was a mix of PDF drawing commands and the actual share data, which in their example was a sequence of numbers embedded within those commands, like numbers representing the ASCII codes, but generated by the XR process.
So they extracted the numbers for the first hidden page.
Yes, they got a sequence like 11, 239, 177, 117, 236.
And then did the same for the second PDF.
Correct. Found the second hidden page, decompressed its stream, extracted the second sequence of numbers 67, 138, 221, 25, 131 in the example.
And a final step.
Perform the reverse of the sharing operation. Since they used XOR, they did an element-wise XOR between the 2 lists of numbers.
So 11 XOR 67, 239, XOR 138, and so on.
Exactly. And the resulting numbers, when converted back to characters using ASCII, spelled out hello.
That is a multi-stage process, but incredibly well hidden, which brings us to detection. How would you even know this is happening?
That's the million-dollar question, isn't it? The paper looks at a few attack vectors, simple file comparison like using diff. Not very useful because PDFs are largely binary.
Right.
But diff with a text option, comparing line by line, might show the change if only the count was modified, assuming you have the original file to compare against. Figure 5 in the paper shows this.
But having the original is a big if in most real scenarios.
A huge if. So without an original, you'd need to analyze the PDF structure itself. Looking for those orphaned objects we mentioned, objects not linked from the root. That could find pages hidden by reference removal.
But not pages hidden just by changing the count.
Correct. That method is more robust against purely structural analysis unless you specifically check the page count against the actual number of page objects or references.
Manual examination sounds painstaking.
Extremely. PDFs have tons of objects for fonts, annotations, metadata. Finding an extra unlinked page object amidst all that noise is hard.
And finding an anomaly doesn't automatically mean steganography, right? PDFs can just be a bit broken sometimes.
That's a key point the researchers make. PDF readers are built to be very tolerant of errors because there are so many programs creating PDFs, not all perfectly compliant. So, finding weird objects or minor errors isn't proof of anything sinister. It could just be a slightly malformed file.
Which ironically makes hiding things easier.
It does. What about file size? Could that be a giveaway?
Maybe, if the hidden share is large relative to the carrier. But the paper suggests aiming for small shares, maybe 1% to 5% of the carrier size, to minimize suspicion. So file size alone isn't a reliable indicator.
It seems this structural method is pretty resistant to content-based attacks, too, like trying to recompress images or alter text.
Yeah, because the hidden data isn't in the visible content, it's in the structure. Those attacks likely wouldn't touch the hidden page object or the structural links, or lack thereof. What about trying to merge PDFs that contain these hidden shares? Does that break it?
They tested that, too. PDF TK sometimes leaked the share content if the page was hidden only by the counter decrement method, but not if the reference was deleted. PDF merged through errors, but still produced a merged file, apparently without revealing the shares, so it varies.
And just randomly messing with the file data to try and destroy the secret.
The paper strongly advises against that for PDFs. They're complex, and random changes are far more likely to just corrupt the entire file, making it unusable, than to selectively destroy a hidden share.
So overall, this seems pretty versatile. Works with different kinds of PDFs.
Yes, that's a major finding. Span documents, text documents, presentations. The method worked regardless of the content type and across all the different software they tested.
Any practical tips from the research for someone using this? Hypothetically, of course.
Yes, hypothetically. Use common-looking documents, ideally ones with a decent number of pages already, so adding one more isn't statistically weird. Keep the hidden share size small relative to the carrier, especially if it's non-text data like an image. And obviously, managing multiple carrier files securely presents its own logistical challenges.
It really drives home why PDF is attractive for this. It's everywhere.
Absolutely. Its ubiquity provides perfect camouflage. The paper concludes this is a solid proof of concept and suggests future work could involve combining it with crypto, exploring other file types, or using even more advanced secret sharing.
Okay, let's wrap this up. What are the core takeaways for our listeners from this deep dive?
I think the main thing is that PDF structure itself can be manipulated for hiding data. By tweaking the page tree, specifically the kids array and the count value, you can effectively make entire pages invisible to standard software.
And distributing pieces of a secret across multiple PDFs using this method makes it even harder to detect.
Exactly. It's resistant to basic checks, content modification attacks, and requires quite sophisticated forensic analysis of the file structure to even suspect something is hidden, let alone recover it.
It definitely delivers that aha moment, realizing these everyday files have hidden potential, for good or ill.
It really does. That hidden complexity is surprising.
It leaves us with a final thought, doesn't it?
Yeah.
If PDFs can hide secrets this way, what about other common file formats or technologies we use constantly?
That's the provocative question. Where else might hidden data capabilities exist waiting to be found or exploited? It pushes you to think more critically about the digital world we navigate, the security, the privacy implications. It's not always what it seems on the surface.
A fascinating and slightly unsettling thought to end on. Thanks for unpacking that research with us.
My pleasure. It's definitely food for thought.